At sea, under the cloak of night, something extraordinary unfolds. Quietly, precisely, and relentlessly, a flotilla of vessels moves across the icy black, laying out invisible grids beneath the waves. Each boat is a node in a synchronized system, guided not by guesswork, but by data. Sonar pulses scan the ocean floor, while GIS coordinates dictate every move. This isn't improvisation, it's orchestration. What's being captured is not just seafood, it's live cargo. And tonight, 10 million crabs are being hunted with a precision that rivals mineral extraction machines, working hundreds of meters below the ocean floor. To most, fishing is a simple act: nets, traps, haul. But when the goal is to extract 10 million living, breathing organisms without breaking the chain of survival, the equation becomes one of engineering, not instinct. The layout of crab pots is calculated with the same geospatial rigor used in subsea mining, where underwater robots must remove ore without collapsing the seafloor. In crab fishing, the trap grid must align with migratory flow, avoid overpressure zones, and time each hole with the tidal pulse. A delay of 30 minutes can compromise an entire load. An error in position can trigger a cascading failure in the night's yield. This is precision harvesting, not of minerals, but of life. Look closer, and the machinery echoes familiar forms from a different world. The hydraulic arms that lower the baited pots mirror the extraction heads of Nautilus minerals, seafloor mining vehicles. Each motion designed to engage delicately with a living substrate. Too much tension, and the crab is crushed. Too little, and the trap fails. The balance is mechanical, but the margin is biological. Unlike ore, these organisms don't just need to be retrieved. They need to arrive alive, intact, and stress-free. The operation is a blend of timing, terrain, and temperature, a mechanical ballet unfolding at the tempo of marine biology. The timing windows are narrow. Crustacean movement is dictated by moon cycles and water temperature gradients. In many ways, this harvest functions more like high-frequency trading than traditional fishing. The data must be interpreted in real time. The pots, hauled and redeployed with surgical cadence. Crews work in silence, not for stealth, but for rhythm. Each vessel is part of a closed-loop system. Position, lift, sort, redeploy, again and again, until the grid is cleared and the sea resets. To understand what's happening out here is to understand that modern fishing isn't a solitary act. It's a logistical matrix, woven with oceanographic data, satellite feeds, machine feedback loops, and the relentless pulse of biology in motion. When the sun rises, those 10 million crabs will be somewhere between sea and shore, alive, cooled, and ready for the next layer of engineering to begin. But before we get to the cold chain, to the oxygenated crates, and the inland race against time, we need to appreciate this. The harvest itself is already a miracle of coordination, a subsea operation where biology, technology, and human timing converge. And all of it begins here, in the dark, beneath the waves, where the silent race to feed the world is already underway. The moment a crab is pulled from the sea, the countdown begins. Not to market, but to biological failure. Every second it spends exposed on the deck pushes it further from optimal quality. To the naked eye, the process seems efficient. Pots are hauled, crabs are sorted, ice is packed. But the reality is less visible. As they lie on steel surfaces, ambient temperatures, sometimes just a few degrees above ideal, trigger a silent chemical shift. Lactic acid builds in the muscle tissue. Oxygen debt begins. Before refrigeration even touches the shell, the damage is already underway. The solution doesn't come from colder ice. It comes from rethinking where cold begins. On advanced fleets, the deck itself is engineered as the first link in the preservation chain. Integrated cooling mats, built into the floor, and calibrated with hydrothermal technology originally designed for high-value tuna, lower the surface temperature beneath the crab's bodies within seconds of contact. The system doesn't freeze, It stabilizes. It mimics the thermal inertia of the seabed, allowing the crabs to transition from water to hold without the physiological shock of a temperature spike. The difference is measurable. In controlled comparisons, vessels equipped with chill floor technology reported a 37% reduction in spoilage within the first 12 hours of handling. That figure isn't just a number. It represents fewer losses, better muscle texture, and higher market value. On these ships, engineers have replaced reactive cooling with proactive thermal control, treating the deck not as a workspace, but as an extension of the cold chain itself. In Norway, one crab fleet retrofitted its decks with cooling mats after losing too much product during warmer night cycles. The change was immediate. Post-catch mortality dropped by half. Onboard holding times extended by 8 hours without quality degradation. For the crew, it meant fewer emergency dumps. For exporters, it meant more reliable inventory. But most importantly, for the animals themselves, it meant fewer stress cycles and greater survivability in transport. We often imagine cold storage as something that begins at the port or inside a refrigerated truck. But in these operations, the first cold room isn't a container, it's the boat deck. And when that surface is treated with the same attention to engineering as any cooling tunnel or blast freezer, the entire logistics chain changes. Because in crab harvesting, temperature isn't just a measurement. It's a material, one that must be shaped, managed, and delivered, beginning not on shore, but here, at sea, underfoot. The trap has been lifted, the deck cooled, the crabs sorted, but between the moment they leave the boat and the moment they enter a controlled cold chain lies a stretch of time that defines everything that comes after. This window, often no more than 6 hours, may appear logistical. In truth, it's biological. During this period, the crab's stress response accelerates. Enzymatic activity rises. Microbial colonization begins. By the time the crates reach a warehouse, the degradation is already irreversible. This isn't a failure of refrigeration, it's a failure of respiration. Without oxygen, the crab's metabolism crashes. Even if the body remains chilled, the internal systems begin to shut down. Standard transport methods, foam bins, wet sacks, sealed boxes, suffocate more than they preserve. What's needed isn't more ice. It's a continuation of the aquatic environment, engineered into the inland journey. Enter the modular reoxygenation crate. Developed from aquaculture holding systems, these containers mimic tide pool conditions. Crabs are housed in low-density stacks, bathed in oxygenated mist or shallow film, and kept in semi-darkness to reduce physical stress. Portable oxygen sensors adjust saturation rates on the move. These crates don't just transport, they extend survivability. In Malaysia, exporters using this system reported a 42% improvement in shell firmness and a dramatic drop in ammonia-induced odors, especially in soft-shell crab batches. It wasn't a change in handling technique, it was a redesign of the in-transit environment, where traditional packaging treats the crab as a cooled object. This approach treats it as a living organism still in transit, still consuming oxygen, still producing waste, still subject to collapse if the chain is broken. In Chile, a crab exporter replaced polystyrene bins with high-density polyethylene crates fitted with oxygen injection ports. Within 3 weeks, pre-export losses dropped by 19%. The reason was clear. The crates weren't passive containers. They were environmental buffers, holding space between marine life and market process, bridging the final fragile kilometers from trap to truck. This phase of crab logistics is rarely seen, rarely optimized, and often underestimated. But it is in these hours, after harvest, before processing, where the integrity of the entire operation is either preserved or undone. Because no amount of downstream refrigeration can compensate for collapsed respiration, cold delays spoilage. But oxygen sustains life. In this system, temperature is only half the solution. The other half is breath. And without it, the cold becomes nothing more than a pause before decline. Modern fishing no longer ends at the net. It doesn't end with the haul, nor even with the sail. It ends with survivability, measured not by what was caught, but by what arrived alive, intact, and fit for consumption. In this shift, crabs cease to be just crustaceans. They become live cargo, and managing that cargo demands the same rigor, sensitivity, and precision applied to any land-based livestock operation. In fact, crab logistics today more closely resemble a floating version of high-performance poultry systems than any traditional idea of fishing. It is the silent transformation of seafood into a living product line, engineered not just for extraction, but for preservation at every step. The challenges begin at the biological level. A crab out of water is not a dormant object. It is a high-risk organism under physiological stress. Once removed from its native habitat, it must be kept cool, but not frozen, moist, but not wet enough to promote microbial activity, oxygenated, but without sudden fluctuations that could induce respiratory shock. Unlike most livestock, which remain in a single environment or are sedated during transit, live crabs experience a succession of engineered habitats. The sea, the deck, the crate, the truck, the warehouse, and sometimes even air cargo. Each stage has a different thermal signature, each one a potential point of failure. To preserve biological viability across this chain, the approach must shift from reactive to anticipatory. It's not enough to respond to spoilage. The system must be designed to prevent it. This is where engineering takes the lead, not only through refrigeration and oxygenation, but through timing algorithms, material science, and environmental modeling. The result is a logistics chain that behaves more like a mobile biosphere than a transport system. The cargo isn't static. It breathes, degrades, adjusts. And so must the equipment that carries it. Take, for example, the comparison to poultry logistics. In advanced broiler systems, environmental conditions are micromanaged. Ventilation rates, feed timing, humidity levels, everything is optimized to reduce stress and improve conversion ratios. In the crab world, similar principles apply. Deck temperatures act as the first microclimate. Transit crates become mobile life support units. Warehouses must modulate airflow not just for cooling, but for off-gassing and ammonium control. Even the truck routes are often pre-programmed to avoid terrain that could cause mechanical vibration and induce exoskeleton trauma. What's at stake is not just product quality, but system efficiency. Every crab lost is a biological investment gone to waste. Every damaged specimen reduces export value and increases per unit energy costs. In this ecosystem, logistics becomes a form of agricultural optimization. It is no longer about moving from point A to point B. It is about creating a coherent pathway through which life can continue to move safely. Some nations are taking this to a new level. In Japan, coastal fisheries have begun integrating biometric monitoring and RFID tracking, not as luxury additions but as standard protocol. Each trap is embedded with location-specific tags that register the time of deployment, ocean depth, and current strength. Once retrieved, the crabs are scanned for biometric indicators: oxygen debt, muscular rigidity, shell tone. These values are uploaded into centralized logistics platforms that use predictive models to determine which batches require accelerated processing, oxygenation adjustment, or route rerouting to reduce mortality risk. It is a fusion of marine biology and data science, a model in which each animal is both a product and a data point. This paradigm doesn't just serve exporters or fleet managers. It redefines the responsibility of the entire supply chain. From the trap to the table, the crab's journey is no longer linear. It's conditional. Every container, every chamber, every transition must be engineered to sustain a living system in motion. That requires more than insulation. It requires feedback loops, systems that sense, react, and self-adjust, whether by injecting more oxygen, modifying airflow, or signaling early-stage spoilage before it becomes visible. What makes this transformation so significant is that it reflects a deeper trend in agriculture and food logistics: the shift from harvest volume to operational yield. Historically, success was measured in weight. How many kilos were brought in? How many containers shipped? But today, the metrics are shifting. It's no longer enough to harvest well. You must deliver with integrity. A full load that loses 25% in transit is not an achievement. It's a breakdown in system logic. And in this logic, the crab becomes a symbol of broader agricultural intelligence. A reminder that even the smallest living unit in our food chain requires a network of design, data, and discipline to arrive safely in front of us. The live cargo is not incidental, it is the test. A test of our ability to sustain life through movement, to match biological fragility with mechanical precision, and to engineer not just for collection, but for conservation. Because in the end, fishing is no longer extraction, it is stewardship through motion. It is the continuous act of balancing time, temperature, oxygen, and intention. It is the art of delivering life, not once, but over and over, through systems that must hold it all together, quietly, relentlessly, and without error. What began as a trap in the sea ends as an engineering victory on your plate. The next time you see a crab in the market, remember the system behind it. Comment 1 if this gave you a new view of food logistics.